Thank you very much for introducing me. So today, I'd like to talk about this statistics. Well, hopefully it's number theory. And let me begin my introduction. So, well, one of the statistics I'm going to talk about is about equidistribution. So let me introduce this notion for those who are not very familiar. So let X be a compact topological space, and Cx is the space of continuous functions. From X to C, and I equip this with zoom norm. And you can consider some variant function space if you like. Instead of continuous functions, you can do something else. And you will consider a sequence of finite subsets in X whose cardinality is going to infinity. And, well, mu is a measure, a nice measure on X, defining a linear functional on the function space. And the definition that xk, the sequence xk is mu equidistributed. Well, that's the case if you consider the average counting measure, well, xk, right? Delta x is the delta measure supported at x. And you say this when this measure has limit as mu, well, as k goes to infinity. And to be a little more precise, what I mean by that is the following. For all f, I take the average of fx on this set, then, and take limit, oops, then that is equal to f mu. So in that case, I'll say that this sequence is mu equidistributed. And as you will see, well, I'll consider this general problem of equidistribution when the objects are coming from automorphic representations. Okay, so let me set some things up. Well, to consider automorphic representations, now I introduce my favorite group G, which I assume to be split just for simplicity of my talk. So it's a split reductive group defined over Q. If you like, actually, you can work over totally real fields, but not in general for some reason I'll explain later. And also I assume that the center is trivial, which amounts to basically essentially saying that I'm fixing central character. So it's not a very serious condition. And I choose T, which is maximal split torus. Defined over Q. And then Fk will be a sequence of families of automorphic representations. And finite families. And according to your taste, you can impose some more conditions like hospital or whatever. And here I also assume that the cardinality blows up so that I can have infinitely many points in my distribution problem. And a typical example, for instance, in the context modular forms will be, for instance, you can take fx to be, say, elliptic modular forms of level nk and weight kappa k, where, well, in the situations I'll consider later, in fact, I'll either fix level and send weight to infinity, or send level to infinity and fix the weight. I mean, you can actually mix. You can vary both arguments, but actually I'll just concentrate on one of the two cases.
I'm sorry, can you still say briefly what you mean by automorphic representations?
Oh, yeah, I mean L2 automorphic representations, and in fact,
what's the joke? Okay, and
Europe novice in the subject, you've never heard of it.
there are many notions. Yeah, so go ahead.
yes, but I mean L2 automorphic representations, and in fact I'll only consider discrete, those in the discrete spectrum.
Yeah,
Right. Wait, I didn't even formulate the problem, so far it could be anything, but I mean, practically only discrete automorphic representations. Yes. But certainly I was embarrassed. It's like Langland's asking me what is functoriality, and but, so sorry. Yeah, so introduce Satake parameterization for local components of these automorphic representations. So for all primes p, well, basically, if you consider all unreified representations of GQP, then you can associate a parameter in the quotient of the dual torus. So this is the Val group, and T hat is the dual torus, a complex torus. So whenever you are given, say, P component of an automorphic representation, it defines a point in here. And if you're more familiar with L parameters, then you just take the image of the Frobenius, and it lands in this T hat. And what's also useful to know is if you look at only those which are tempered inside here, then they correspond to some subset where T hat C now is the maximal compact subtorus. So when this is like C cross, then this is like the circle U1. Right? Okay, so with this preparation, I can state two questions for families of automorphic representations. So for the first one will be Sato-Tate. kind of version of Sato-Tate, but for families. So for this, I choose sequence of prime numbers, and of course, I will look at Satake parameters at these primes as k is going to infinity. So the question is about the equidistribution of, say, pk component for all pi in fk. Oh, by the way, I forgot to say, but, well, in general, somehow I want to take fk to be a multiset. So the same representation may appear more than one time, which is very natural from automorphic point of view. I mean, at the very least, there may be automorphic multiplicity, and then I want to take that into here. So in any case, so if this is multiset, then you can just count the same representation according to the multiplicity. And this is a finite set because fk is a finite set, and then when k is going to infinity, I get a nice sequence whose cardinality is blowing up. And I can ask about this equidistribution problem on here. I mean, regardless of my prime, they all define some points on t hat modulo the Weil group. So, for instance, are they equidistributed according to some natural measure on this space? That's the question. And the second question, which I'll be very brief about, well, seemingly the question is of very different nature. It's about low-lying zeros. Well, what zeros do I mean? It's zeros of automorphic L functions. So you take some representation of the L group, and, well, you make a big assumption that this L function is automorphic for all k and for all pi in fk. Well, for instance, if you believe in, well, Langland's functoriality for this R, then.
I'm sorry, that's a silly question again.
Yes, I'm nervous again.
Automorphic, you mean on the natural GLN? That's what you mean?
Right, yes. Yes. Automorphic L function of standard automorphic L function. Maybe it's, yes. I just, it's basically, well, more or less the same thing, but if I say that assume Langland's functoriality, then it sounds more serious. So, yeah. So that's what I assume is automorphic L function of some GLN or GLD. Okay, so what do I want to ask here? Well, I mean, it's very roughly stated, but what is the distribution of the zeros of, well, pi r near t equals 0? Right? Not this, sorry, pi in fk, as k goes to infinity. Well, if you believe in this, well, generalized Riemann hypothesis, then basically all the zeros will appear in the central line, but you don't look at all zeros, but those which are very close to the real line. And near t equals 0, well, basically means, I'm not going to be precise, but it means that T is bounded by some constant multiple of 1 over log of conductor of analytic conductor of pi. But if this doesn't mean much to you, then you can just forget it. Because I'll be focusing on the first question most of the time. Okay, so now that I formulated questions, I'll tell you. Oh, I forgot to. I had to. This is all joint with Nicolas Templier. Sorry about that. Yes. Somehow. Right. So are we in 1.5? So main results. Well, results are the following. Assume that for all k and for all pi in fk, pi has discrete series at infinity. Otherwise, well, experts will notice that, I mean, this makes some simple form of the trace formula available. So it makes lots of computations easier. Otherwise, well, it's more technically much more demanding. So I assume this. But that's the only essential condition. And there are some smaller conditions which I'll make precise later. Under a suitable condition, and this condition is on the rate of the primes approaching infinity. Somehow I have this condition. Under this condition, we can show this equidistribution according to the Sato-Tate measure. Well, what do I mean by Sato-Tate measure? Sorry?
You'll have to define what you mean by that.
Yeah.
I don't think it's a generic form of that measure.
Yeah, it's the Sato-Tate measure. Yeah. Yes, yeah, I'm going to define which is this. G hat C is the maximal compact subgroup of the dual group of G. So here I have Haar measure, say with total volume 1. This is compact group. And for each element, I can associate an element here basically by looking at its conjugate class. Conjugate class intersects this torus and defines a well-defined conjugate, well-defined element here. And you just push forward the Haar measure. Under this surjection, you get this Sato-Tate measure. So that's the measure I'm talking about. And well, my answer to the first question is that under suitable condition, and of course, it depends on what families I'm going to consider. But for those families which come from basically the automorphic spectrum as I let level or weight go to infinity, as in my previous example, for those families where level and weight go to infinity, well, basically Satake parameters are equidistributed according to the Sato-Tate measure. So this is different from a Sato-Tate conjecture for an individual representation, but still, well, qualitatively it means that generically members of the families of automorphic representation follow the Sato-Tate, well, Sato-Tate law, if you like. So,
Physicists have another name for this measure?
I don't know. Is there?
I don't know.
I guess they have names for all sorts of things, but well. But I'll make this statement more precise later. So for now, I'll content myself with this. We are still in introduction. And as for question 2, well, the result is not quite complete. What I can say is, using some jargon, well, one level density for these central zeros, low-lying zeros, kind of coincides with the prediction from random matrix theory. But I'm not going to say anything more than this. And it's not completely proven at the moment. There's some, as usual in the automorphic business, there's some issues with poles. Somehow, we haven't shown yet some contributions coming from poles are negligible. So there's some issues. But hopefully it will be removed soon. So in any case, today I'll focus on the first question only, but it's worth mentioning that, well, why do I consider these two problems at the same time? Because they are very closely related, although seemingly they are very different. So I just remarked that I mean, the method of proof is very closely related. Okay. Yes.
You don't have to know in advance that your representations are tempered?
Right. Well, because we're working statistically, what happens is that, well, generically, these representations are tempered. In the families I'll consider, you can actually prove that, well, generically everything is tempered, and that basically follows from the fact that Plum-Sherrill measure is supported on the tempered spectrum. But yeah, you'll see in a little bit. Okay, any other question? All right, so, and before ending this long introductory part, I'll show you some heuristics for the first question and some related questions. So here's what I would call Sarnax diagram from Harry's bar. The rumor has it that, well, I was present, but he drew some nice diagram on a napkin in Harry's bar, and I'm trying to reproduce this diagram. Okay, so here I put prime numbers p on the x-axis, and here I put k. But as k go to infinity, in my families of automorphic representation, what happens is either weight or level is going to infinity. So you can consider 3 different questions. Well, what happens to my Satake parameters if I fix prime p and let the families grow to infinity, or you fix your automorphic representation and then just let prime go to infinity, or you can just do something intermediate. So what happens is, well, let's call this A, C, and B. Well, what happens is, this what we observe is that, I mean, there's some borderline, so that if you're above this border, then actually this limit will be Sato-Tate. Basically, whatever path you take. And this direction, we know that according to the well-known conjecture, is the Satake parameter should be equidistributed according to Sato-Tate measure.
That's false.
Well, but then, yeah, one has to be careful. I mean, what measure are we talking about, right? So, yes, I mean, naively stated is false, but I guess one has to impose some extra conditions to make it true. Even for GL2, you have to exclude CM forms. I mean, CM forms and other modular forms follow different statistics. And here, well, you fix prime and then you just look at Satake parameters at the same place. And here, the answer is actually different. In this direction, you always get Planck-Scherl measure as the answer. So,
in case A, are you letting the level go to infinity by increasing the level at a prime that's not the prime that you've chosen? Or
oh, yeah, that's a good question. I'm actually, yeah, in this case, well, in fact, it's okay to allow ramification at the prime, but let's say for later purposes, primes are always prime to my level. Let's say that. But for the vertical direction, in fact, it's okay to allow ramification at P. Okay, so let me say briefly about this ABC. Well, in this direction, well, I guess still, well, I shouldn't say much, but I mean, well, yeah, we know, well, what's the kind of fair thing to say here? Well, we know some cases. Well, many cases are known, in fact. And here, B is actually what our work is about. Well, at least when the question 1 is concerned. And then for C, I guess nothing is known beyond GL2. And well, here there's a very long, interesting story, and there's some history as well. But as far as I can see in the literature, previously B was proven only for GL2. I'm not sure if is that right? GL2 case, yes, basically due to Cornelius Duke, Farmer, and Serre in late 90s. And in this direction, there are more results, and well, we don't know much about C. So in fact, if you look at the proof, then the difficulty is increasing in this direction. So for A, well, basically the trace formula will handle the problem plus some minor effort. Here, you need trace formula plus some major effort, and here I guess, well, I guess David can tell. This so far is very difficult, and only arithmetic machinery seems to have success. Although, I mean, in principle, this should follow from Langland's functoriality. Okay, so, all right, I still have enough time, I guess. So that's the end of introduction, and I'll start making more precise statements. Yes?
To me, so far, B is undefined because you draw a kind of parabola, but there are many parabolas.
Yes, so that's true, but I mean, in the result, I'll show you what kind of, I'll talk about this kind of borderline, and then I'll formulate the result, well, relative to the borderline. Yeah, it's kind of a graph. Graph of, well, a function given by function of level in terms of prime or weight in terms of prime. Yeah. So yeah, I'll show you something more precise. Okay, so let's set up some more notation. So UN will be level n subgroup. So it's G z hat, G z hat mod n z hat. And there's a weight parameter, which will be in the character group of T, but plus means dominant weight. And I try to assign magnitude for this psi, which is the minimum value of alpha psi plus rho. Using standard notation, phi plus means the set of positive roots. Rho means the half sum of all positive roots. And that will be some positive number. And let's see. And I introduce notation for the Plancherel measure. Let's write mu hat PLP, PL for Plancherel. I apologize for not defining this measure. It's some measure defined on the unitary dual of GQP, the set of unitary representations of GQP. And, well, I choose S, a finite set of primes. And for convenience, I write mu S to be product of P in S of product of these Plancherel measures, and capital P S will be product of primes in S. So that's my notation. And now I'll be more precise about the kinds of automorphic families I'll work with. So two kinds of families. So I call them F1 and F2. So first of all, Fk will be defined as the automorphic, well, say hospital automorphic, or you can use discrete representations of GA with, we'll say level, which one goes which, U. Say level U and K and weight kappa or psi, or with the same thing, but you fix level and weight is a variable in K. So, and in all these cases, nk go to infinity, or weight, to be precise, m of the weight goes to infinity as k goes to infinity. And if we do that, we know that there are infinitely many automorphic representations. So the problem makes sense here. And they're kind of very natural families you can think of whenever a group is given. And well, just one wrinkle here is that, well, I assign some multiplicity of pi in this family. I told you that these will be, in general, be considered as multisets. So this, I should tell you in what multiplicity each pi appears in this family, and that's given by this, well, automorphic, discrete automorphic multiplicity, or in fact hospital, times, sometimes it comes with some extra factor for some technical reason. Well, for instance, it could be the dimension of the fixed vector under this level subgroup. So that's a little technical point, but somehow things are easier to estimate in this way. It's just saying that when you consider modular forms, instead of considering new forms, you consider just all the eigenforms. So actually the same representation can appear multiple times. Okay, and given these families, define a measure on unitary dual of GQS. QS means product of QPs. And it's enough to look at the unreified part. And how do you define a measure associated to this family? Well, again, you take the average counting measure, where you count the S component of each automorphic representation. Yes?
You just said this, but you're saying you're counting all forms as well. It's not just a single vector.
Right. Yes. This. So that multiplicity is encoded in this number. So when we think about equidistribution of S components of these families, it's just about the limiting behavior of this counting measure. And okay, so now I'm ready to state the key result. Well, first of all, let me.
So we don't know that it's unramified, that it's supported on
Yeah, I think I forgot to say. Well, for the purpose of the talk, I'll always assume that S is prime to level, but I guess I didn't say. So, yes. And S is not something fixed. In fact, the whole point is to let S vary. So it's some finite set which can move around, but avoiding any clash with the level. But okay, so well, thank you for reminding me. And now let me define just one more notation. So so I want to associate for each unreified Hecke algebra of GQP element, say phi p, I want to associate a function on the unitary dual. How can I do it? There's a very standard way, which is that if you have an unreified Hecke algebra element and an unreified representation, then you just take the trace. So because in all these discussion, measures are fixed. For instance, you give the hyperspecial maximal compact subgroup measure 1. Okay, so this, now I'm really ready to state a theorem. And this turns out to be, in fact, a common ingredient in answering question Q1 and Q2. Okay, so let's, well, I already assumed that S is prime to level, so I don't have to repeat. Okay. For unreified Hecke algebra element, there exist some positive constants. And the point is, these are independent of S, such that if you take the difference of this counting measure and the Planck-Scherl measure, then it's very small. And moreover, it's very well controlled. So it's like nk to C1. No, I think it's the other way around. PS C1 and k minus C2, or PS C1 and m psi k minus C2. Is it readable? So in each case, F1 and F2. Yes? Yes. Oh, it doesn't depend, but I'm. Yeah. So yeah. Sorry. Yes. Exactly. Sorry. Yeah. It shouldn't be in the notation. Thank you. So the theorem is that, well, basically this measure tends to the Planck-Scherl measure at S, some natural measure coming from representation theory. And the difference is bounded by some power of the primes times negative power of level, or power of primes times negative power of the weight parameter. And yeah, somehow this is very nice.
I don't understand the
Yes.
statement. Phi s is fixed.
Phi s fixed. Yes.
How then can the statement be independent of s?
So yeah, using Satake isomorphism, I can. Phi s defines an element in here, which is
For a finite number of primes. I mean, if
yes.
I give myself phi s, basically I have
Yes.
a
Oh yeah. I should. Yeah. For instance, I mean, the cardinality of s should be fixed if I move around. But in fact, I state this result in a kind of more refined way. But here you can just think that the cardinality of s is actually fixed. That's what I'm going to do in corollaries. So, and then so.
S of cardinality n, I erase independent of s. This statement is true with absolute constants.
With absolute constant. I think it's.
I think you should give the exact conditions.
Yeah. Well.
That the degree is fixed.
Yes, but I think it's actually in the. I think it doesn't depend. I mean, the only dependence on s comes from the fact that there is ps in this bound, but it doesn't. If I formulate in a more refined way, then actually it doesn't depend on the cardinality of s. And the way I
Why don't you write this just independent of cardinality of s?
But I still don't
also, but I mean, the actual set s also independent of the set s.
I still don't understand logic in some sense because giving phi
Yes.
will be a finite tensor product.
Yes.
Giving phi essentially tells you where it's a unit and where it is not a unit. So phi defines s.
Yes. So I guess this is probably not a good way to state. Well, in the actual statement, okay, well, maybe I'll give you an alternative. So in fact, I mean, the way I actually do it is I define truncation and then I don't mind what s is. I just make it independent of kappa and also s. But then for that I have to define truncation and then I try to avoid it. But maybe that makes theorem less transparent. So yeah. Okay, so well, going back to the theorem, well, yes.
Once you use the truncation, do you still use PS or is there some function of k that you use?
Could you say again?
Expression, is it still a PS?
Yeah, just PS and yeah. I mean, the multiplicative constant implicit in this big O and then C1 and C2, they are all independent of this data. So that's.
C1, C2 depends only on K. They're independent
Of K,
of kappa.
kappa. Well, C1. Oh yeah, C1 depends on.
Only on kappa.
C1 depends on kappa. C2 is independent of kappa. Yes. Oh. Yes. If I put kappa, then I should put kappas here. So, yeah. Thank you.
Then the absolute.
Yes.
Then it's absolute.
Yes. Then everything is now independent. Yes. Yeah, before I try not to talk about truncation, but now that I said it, I should put them in there. Okay. So the corollary. Apologize for not defining this, but I mean, it's kind of something intuitive. If you look at the image of the Satake transform, then there's polynomial algebra there. So it's almost like looking at the degree of the polynomial in the Satake transform. But I'm not going to say anything more than that. So the first corollary is Planck-Scherl density, which was our graph A in Sarnak's diagram. So this is in fact very easy. You just take limit and you get this Planck-Gérôme measure. And well, of course, this will disappear because nk or this m psi k will go to infinity. And well, this actually, I was proven this in the same generality or about a year ago or more than a year ago. But then this stronger version will imply kind of product Sato-Tate. And it's about graph B, but what's good about this is now you can consider several places at the same time. And in the original Sato-Tate conjecture for, say, individual modular form, this product Sato-Tate conjecture is very difficult if there are more than 3 modular forms, I guess. That's what. I mean, it's not. Sato-Tate at 3 places.
3 forms or 3?
Oh. Yeah. I think yeah, both are good questions. But yeah, 3 places, I guess. Okay. Well, never mind. I see.
Beyond that, it no longer.
I see. I guess yeah, it's a different question. Yes. Yes. Yeah. Here I don't consider 2 forms at the same time. It's only at 2 different places. So, but for the interest of time, maybe I don't know if it's difficult to state. Let's see. Well, let me just state. I consider a sequence of primes, sequence of m tuples of primes, and of course this will go to infinity if k goes to infinity. And the contents of the corollary is that for all I, if these guys go to 0, or this m, then Satake parameters are equidistributed according to the Sato-Tate measure. So I'll say say f equals mu Sato-Tate. So mu Sato-Tate is the Sato-Tate measure, and it's just saying that, Satake parameters, remember that this is a counting measure, so Satake parameters at this m tuple of primes, as these primes go to infinity, the Satake parameters there are equidistributed according to the Sato-Tate measure. So, and these are measures on, m product of m copies of this torus quotient. Okay. And why does this follow from the theorem? Well, basically you take, what's clear is you take S to be this, a set of m primes. But what's important to know is that the basic principle is if you let p go to infinity, then Planck-Scherl measure has the Sato-Tate measure as the limit. So and this is in fact quite easy to prove once you have the exact formula for the Planck-Scherl measure which is available. Once you combine that, then whenever this element comes from unrarified Hecke algebra, you can prove this, and then you use the fact that the unrarified Hecke algebra generates the dense subspace in this function space. So that proves the question 2, given that these conditions are true, and these conditions basically mean that in the previous diagram, you're moving along some parabola above some certain dotted line given by this or this conditions. Okay, so so the whole discussion comes down to justifying this type of theorem. Now, in the remaining time, I'll explain proof as much as possible. So so first of all, there's you got to use trace formula in any case. That does the initial job. So remember, we have this counting measure for S components in the automorphic families. And using the trace formula, a priori you can prove that this is equal to some for some test functions. You can prove this equality, and the way it works is this part will take care of this average times this multiplicity of pi in the family, and then this corresponds to 1 or minus 1 depending on your sign convention. This is Euler-Poincare function picking out exactly the representations which have the same parameter as this weight parameter. And this part will be exactly this. If you think about it, is the delta measure evaluated on this phi hat S. So you see that it exactly looks like our counting measure before. So you first prove this equality, and then, now that this is exactly the spectral side of the trace formula, now you can go to the geometric side and compute every term you see there. So this I'll say that what you get is you have an expansion over some Levy subgroups and rational conjugates classes, which are elliptic in M of R, times some volume term associated to the centralizer and some orbital integral away from infinity phi upper infinity means away from infinity, and phi m means this means constant term along m, or the associated parabolic. And there is also some expression at infinity, which is a, say, stable discrete series character associated to this weight parameter. Right now I'm sketching the proof in the weight case. In the case weight varies, so it's the case of F2. I mean, you can basically play the same trick for F1. Okay, so you get this expression, and that's so much as the trace formula can help you. Now you encounter this expression, and then you have to evaluate. Well, fortunately, it's not difficult to pull out the part relevant to Planck-Charel measure. In fact, it's not hard to show that when m equals g and gamma equals 1, then you get this as a main term. But then you are left with everything else. And the whole question when you try to prove this theorem is you have to control this, and we'll try to evaluate, estimate to show that they are bounded by these expressions. Now, how do you do it? Well, now I'm running out of time, so I'll just say in word. For the volume term, well, unfortunately, this should be somewhat easy, but it involves some values of RTNF functions at s equals 1, depending on your convention. So you got to estimate that, and you have to estimate these orbital integrals. And remember that the difficulty here is you want some bound independently of the place S. So when your conjugate class is moving around and function is changing a little bit, you have to get a uniform bound on this, and this is actually easier to handle. And finally, you have to also estimate the number of conjugate classes meeting the support of these functions, and then that you also have to get a uniform bound on. And after doing all this, you just multiply them out and do some computation, you get these bounds. And in fact, this evaluation of these terms is at the core of proof. And I'll stop here. Thank you.